Hello and welcome back. In today's video we will design and implement a simple, but very interesting, IR detection circuit that acts also as a switch by using two components, IR LED QED234 and IR receiver QSD123. In two previous videos we have covered in every detail all that there is to know about these two components, so we actively encourage you to watch those two videos, as they are the prerequisites for understanding topics we will cover in this one. Our goal is to generate electrical signal that can be used to control other components in the circuit, like indicator LED, or a signal to trigger integrated circuit of particular function and usage scenario, or a relay that can switch on and off some other load. If you enjoy practical electronics tutorials like this one, please subscribe to the channel. Don't forget to like the video and enable notifications so you don't miss future projects. Thank you. Our goal is simple. We need to choose components to design and implement electrical circuit that is based on IR detection. This is the idea. We have infrared source, the infrared light emitting diode, QED234, and we have infrared receiver, QSD123. Together they form a detection circuit. When both powered on, the LED emits beam of invisible IR light that irradiates receiver, which is for all intents and purposes, a NPN transistor in nutshell, and drives it into active mode of work. When beam is interrupted by an obstacle, for example, a person walking, the detection circuit is interrupted, receiver goes into cut-off mode of work, and signal is generated by detection part of the circuit that announces that there was a triggering event. Now, how and why did we choose components the way we did? The choice of IR source and receiver is obvious, and based on our two previous videos, as these two components represent ubiquitous source and detection components for IR detection circuit. Next, the power source. Rule of thumb is to use power source of minimum voltage and minimum current that will satisfy design parameters and provide necessary power to circuit's components without unnecessary waste in form of heat dissipation. Since our design will use indicator LED that has voltage drop of around 3 volts, we must go a little bit higher than that, so our next best readily available choice is 5 volts. Choice of 5 volts will satisfy requirements for voltage drop for indicator LED. Also, it will provide necessary bias voltage divider for detection circuit, and at last, it will provide enough voltage to bias and power on all other components in the circuit. As for the signal after triggering event, we will use change in voltage from low to high, to signal to the rest of the circuit that triggering event has occurred. In our case, change from low to high means change from 0 to 3 volts. The rest of the components will be familiar NPN transistor 2N3904, and 3 resistors, one working in tandem with IR receiver to form voltage divider circuit, and 2 others for current limiting purposes, connecting wires, and LED indicator. Before we continue, in order to understand why we made following choices for voltage, current and resistors, it is of paramount importance that you watch previous 2 videos, where we cover in detail electrical characteristics for IR LED and receiver. Those videos go over every possible detail in datasheet parameters, maximum and recommended values for voltage and current, and other parameters for choice components. First, the infrared source. This part of the circuit consists of QED234 infrared LED and current limiting resistor. From datasheet parameters we know that maximum current we can run through the diode is 100 mA, but that is only for pulse DC power source. Since we have continuous DC power source of 5 volts, the maximum value we could run would be half of maximum recommended value. To be on safe side, to prevent unnecessary heat dissipation, and to prolong component's life, we will use 1/4 of recommended maximum value. Our choice of current will be 25 mA for source part of the circuit. From datasheet we know that voltage drop over IR LED is 1.4 volts, when using 5 volts as a power source. By using Ohm's law, we can get necessary value for current limiting resistor R1. We get value of 144 ohms for current limiting resistor R1. Since this is not standard value, the next best thing is standard 150 ohms resistor. Also, let us remind ourselves that power dissipation of IR LED and resistor is 100 and 125 milliwatts, respectively. When we plug in the numbers for power heat dissipation, we get 35 milliwatts for diode and 90 milliwatts for resistor. Since both values are well within limits, we are safe to continuously use this part of the circuit without any worries about overheating and heat dissipation. Everything is well in the green. Next, we have infrared receiver part of the circuit. This part consists of infrared receiver QSD123 and current limiting resistor R3. From QSD123 datasheet we know that in order to drive phototransistor in active mode of work, when using power source of 5 volts, we need 0.5 milliamperes current and 0.5 milliwatts per square centimeter of infrared light. From datasheet we also know that when phototransistor is in saturation mode, voltage drop across collector-emitter terminals is 0.4 volts. So, with all of this, by using Ohm's law we can calculate value for current limiting resistor R3. We get value of 9200 ohms, which is not standard value for resistor, so we go for next best value, and that is standard 10 kiloohms resistor. Also, quick power dissipation calculation for both components give us values of 0.2 and 2.3 milliwatts, for phototransistor and resistor, respectively. Everything is well in the green. Now, the logical question is, why the resistor is not placed before phototransistor in the circuit? If you know why, pause video, leave the comment, and then proceed, because we will explain this right now. Assuming that there are no alternating current power sources, capacitors, or inductors in the rest of the circuit, we can replace entire portion of the circuit with something called equivalent resistance. So, we can replace entire portion of circuit containing LED indicator, resistor R2 and NPN transistor with equivalence resistor RE. So, when we power on this equivalency circuit, where and how will current flow through each branch of the circuit? We designed the circuit so that IC is 0.5 milliamperes and resistor R3 is 10 kiloohms. Now, when we power on the circuit, current IC will split into two currents, I1 and I2. The sum of I1 and I2 must be IC, or current laws fly out of the window. What we do not know is the resistance of RE. From looks of the things, RE is basically base current limiting resistor for NPN transistor 2N3904 from original circuit, right? Now, in order not to overcomplicate this video, we will just accept that some very smart people have calculated this RE is internal base emitter junction resistance, without small AC signal present, and experimentally determined that, for small power sources, and small currents, its value ranges from couple of hundreds of ohms. Now, since RE is much smaller than R3, by factor of 1000 at least, that means that current I2 is much greater than current I1. Now, here comes that famous loophole. Since current I2 is so much greater than current I1, we can safely disregard I1 entirely, and say that all of the IC goes into RE, and that for all intents and purposes I1 is so small, that we can equal it to 0. In order not to do disservice to our viewers, to be absolutely precise, I1 is never 0, and I2 never absolutely equals to IC. We make these assumptions to make things easier for us. Also, margin of errors, introduced by imperfections of components, provide cover for these assumptions. To summarize it, current IC is the same as current I2, since RE is so much smaller than R3. The current IC now represent biasing current IB for NPN transistor. The base current of 0.5 milliamperes is quite enough to drive NPN transistor into active mode of work. Now, let's get back to our original question. What would have happened if phototransistor and resistor are 3 swap places? Again, current IC should split into currents I1 and I2, right? Let us remind ourselves that when phototransistor is in saturation mode of work, voltage drop across its collector-emitter junction is 0.4 volts. That implies that its equivalent internal resistance is very small. Basically, it acts as a closed circuit. Also, let us remind ourselves that current always take a path of least resistance. So, in this case, phototransistor provides little to no resistance to current flow at all. On the other hand, resistor Re is small, but it provides some resistance that is greater than other path current can take across the photoresistor. So, in this case, there will be no branching of current IC into currents I1 and I2. Entire current IC will sink into ground, and no current will flow into Re. This will produce no base current IB to bias NPN transistor, and the NPN transistor will remain always in cutoff mode of work. The circuit will never be on. To be absolutely precise, there is some internal resistance for phototransistor, and there will be some branching of current IC into currents I1 and I2. But, resulting current I2 will be so close to zero, that we can safely disregard it. It will never be able to provide enough biasing current for NPN transistor. If you have watched our previous videos, this part will be very easy to understand. This is simple setup for NPN transistor in saturation mode of work. Biasing current IB is provided from phototransistor, when phototransistor is in active mode of work. We designed the circuit so that biasing current IB equals to 0.5 mA. This is enough to drive transistor in active mode of work. We will assume beta, or to be more precise HFE, with capital FE, to be 200. Remember, that HFE with capital FE is ratio between collector and base current. Episodes 13, 14 and 15 cover this topic in all possible details. So, if you are not familiar with this topic, those episodes are your source of information about this topic. For HFE parameter of 200, the resulting collector current will be approximately 100 mA. Since the load we wish to drive with this configuration is simple indicator LED, we must limit the current power to less than 20 mA. That is maximum current our indicator LED can take. But to be on safe side, and not to overheat indicator LED, we will limit the current to less than 15 mA, by using resistor R2. So, let's do the math. The VCE power source is 5 volts, we will assume voltage drop of 3 volts across the indicator LED. By using Ohm's law, we have value of 133 ohms for our 2 resistor. Since this is not a standard value, we will go with next best thing, the standard 150 ohms resistor. So, this part of the circuit is complete. Let us also do a quick power calculations for all of the components. The resistor R2 can dissipate 125, and LED can dissipate 100 milliwatts, so, when we do the math, we are well within safety limits for both components. Also, maximum collector current is limited to less than 15 mA, so that is well below 150 mA from NPN 2N3904 datasheet for maximum safe collector current. Also, for simplicity of calculation, we have disregarded voltage drop across collector-emitter junction, as it makes no real big difference in calculus. When in saturation mode of work, this voltage drop is around 0.2 volts. So, our circuit is complete. All of the parameters have been defined, assigned value, and their function in the circuit explained. Now, let's see how we generate signal for triggering event. Let's assemble and power the circuit. Our infrared diode will irradiate the receiver. The receiver will go into saturation mode of work. It will generate biasing current IB for NPN transistor. When NPN transistor is in active mode of work, it will provide enough collector current to power indicator LED. The circuit will continue to function, until some triggering event disrupts infrared beam of light and causes receiver detection part of circuit to power down. From what point in circuit can we draw signal voltage? Let's mark all possible junction points with numbers from V1 to V4. Clearly, points V1 and V4 are directly connected to positive and ground terminal of the power source. Their potentials are always 5 and 0 volts, respectively, and state of the circuit has no impact on them. The only remaining two possible candidates are points V2 and V3. Their potentials change with the change of state of transistor. No matter if transistor is in cutoff, active, or saturation mode of work, we always take output signal at collector junction, if there is a load above. When our NPN transistor is in saturation mode, this junction will have saturation voltage, in reference to ground. We know from datasheet, that saturation voltage is between 0.2 and 0.4 volts. This means, when our detection circuit is powered on, junction V3 will provide continuous DC signal with amplitude between 0.2 and 0.4 volts. Since this is very small voltage, we can round it down to 0 volts, and call this output a continuous low signal. If we place multimeter probes at collector junction, in reference to ground, our multimeter will show voltage of around 0.3 volts, when detection circuit is powered on, and there is source of infrared light. What happens when there is a triggering event? First, let's define a triggering event. By definition, the triggering event is external influence on the circuit, that causes the circuit to change from one state to next. In our case, triggering event will be physical disruption of infrared beam. This will cause infrared receiver to go into cutoff mode of work, which will for consequence have that there is no more base current IB to bias NPN transistor, which will for consequence have zero collector current. Our NPN transistor will go into cutoff mode of work, and amplitude of our signal at point V3 will jump, from saturation voltage of 0.3 volts, to difference between power source and voltage drop across the resistor R2. That is 5-2 volts, which gives us high signal value of 3 volts. When infrared beam resumes, the circuit will revert to previous state, and signal will drop again to low state. So simple, yet so effective. If we were to hook up our S01E19 oscilloscope at point V3 in our circuit, we would observe signal that would look something like this. One practical implementation of such circuit would be as a counter of passing. If we were to position our circuit so that whenever person, or some other object, a car for example, passes through the detection corridor, the infrared beam would be interrupted, and triggering event would occur. We could use this signal as a triggering event for another circuit that would be based on some integrated circuit with counting function. In this manner we could count the number of people or cars that enter or exit a premise, for example. Further analysis could provide more analytical data, such as frequency, peak hours, and etc. In our next video we will implement this design using breadboard for prototyping and components defined in circuit design from this video. We will also hook up our oscilloscope and simulate triggering events, to see the shape of our signal, so stay tuned. Please, before you leave, show your appreciation by liking this video, leaving a comment, sharing it, and please subscribe to the channel. Thank you, and see you next time. Bye.